Hello, welcome to the chapter on acids and bases. Let me start off by talking about some common acids. So, hydrochloric acid, also known as muriatic acid, used for metal cleaning. You use it in pools. Also, stomach acid. So, stomach acid in our own bodies, we have hydrochloric acid. It's in our stomach. Sulfuric acid. This is also known as battery acid. Car batteries. Are also known as lead acid batteries. Use these. The primary use for this is fertilizer. Something you'll notice for it's used for other things. So sulfuric acid, explosives, batteries, electroplating, and then the nitric acid, fertilizer, explosives. But about three-fourths of acids and bases, what they're used for, is to make fertilizer. so if you look at what we make as a society, the most we make of anything is transportation fuels. That's number one. Number two, agrochemicals. So fertilizers, pesticides, and of those we make a lot of fertilizers, and we do that because we support a population. We have, uh, gosh, I don't know how many billions of people we have now. 8 billion. All those people, 7 billion, 8 billion. The reason why we have so many people is because we can feed them, and specifically, it's our industry that we've mechanized our agriculture, which allows us to have such a huge population. And nitric acid, so sulfuric acid we make quite a bit of. Nitric acid we make a little less of that, but it's dangerous. Nitric acid is actually something that we track. It's a controlled substance, and you tend not to see it in chem labs either, because if you mix nitric acid with stuff, it tends to make explosives. Dynamite is made from a chemical called nitroglycerin. So how do you make nitroglycerin? Take glycerin and you mix it with nitric acid. Maybe you've heard of TNT, that's trinitrotoluene. How do you get that? You take nitric acid and you mix it with toluene. So nitric acid can be used to make explosives. And the ammonium nitrate is a very common fertilizer. It's also used in explosive. Acetic acid, this is the primary component of vinegar. Used many things, food preservative and various things. Citric acid, it's used in food. I mean, it's already in limes and lemons and that kind of thing. And can be used as a buffer. Sodium citrate can be just the pH of things. Carbonic acid, we find this, well, it's in carbonated soda, and we use it in our own bodies. It's how we can take carbon dioxide and bring it to our lungs to exhale. Hydrofluoric acid, this stuff scares me. It's scary because if you get any on you, it goes right to your bones. It'll eat through your stuff till you get to your bones. It'll dissolve glass. So if you ever see frosted glass, it's frosted because of hydrofluoric acid. Used to clean metals too. So scary, scary stuff in my opinion. Phosphoric acid used to make fertilizer and also as a buffer and added in food. Those are acids. Oh, and you notice here that acids, they're red. Acids turn a indicator called litmus, turn it red. Acids also, they work by adding positive charge to things. Biological surfaces are negatively charged, so if you add an acid to a biological surface, it tends to shrink it. And acids taste sour. So acids taste sour. Bases, on the other hand, bases taste bitter. They term litmus blue. So you can make salt, sodium chloride salt, by mixing hydrochloric acid and sodium hydroxide. So bases taste bitter. And what does bitter mean? You ever drink medicine like cheap NyQuil or like cough syrup that has no flavor enhancements in it? You taste stuff like, it's horrible. That's bitter. Bitter is a bad taste. Sour, people tend to not like sour. You can teach yourself to like it, but generally speaking, humans don't like sour and bitter, especially bitter, because things that are poisonous tend to be bitter. So caffeine is very poisonous. Because, we take caffeine, but like a cup of coffee has 100 milligrams. Milligrams, zero point 0.1 grams. If you take a lot of caffeine, you will die. So nicotine, a lot of the caffeine and nicotine, they're molecules known as alkaloids. So they're alkaline. Alkaline means basic, and they're made by plants. So, and bases taste bitter. So sodium hydroxide, I've never tasted it, but it would taste very bitter. Hydrochloric acid, I've unfortunately tasted that because I've thrown up before. I'm sure everyone's thrown up in his or her life. I know that it tastes really sour, it tastes terrible. But salt doesn't taste bitter, doesn't taste acidic, it tastes salty. So salt is no longer got the properties of an acid or base. But sodium hydroxide, this is also known as lye, L-Y-E, used to work in petroleum, used in soap. How do you make soap? You take fat and you mix it with lye, and then that forms soap, which is sodium surfactant, and then you get glycerin. So you can keep the glycerin in the soap, or you can take it out and do other stuff with it. Potassium hydroxide, still done in soap production, used in batteries, alkaline batteries, used for cotton electroplating. Sodium bicarbonate, we tend not to use an acid anymore. That's what's in baking soda. And sodium carbonate, this is washing soda. It can be used to make glass and soap. Yeah, sodium carbonate plus silicon dioxide greatly reduces the melting point of glass. The ancient Egyptians figured that out. If you ever use OxyClean, that's what's in OxyClean. Ammonia uses a detergent, so fertilizer. Primary use is fertilizer. You can use ammonia. You can burn it to form nitrogen oxides, and then you can hydrate that to form HNO3, so nitric acid. So, but again, ammonia's primary use is fertilizer. It's a number 2 in the list, but its really primary usage is fertilizer. So we should probably talk about what an acid and base are. So Arrhenius, the Arrhenius acid base, it forms hydrogen ion or hydronium in water. So I've drawn the water here. So this is my water molecule. And if you have, it's like a Mickey Mouse. If Mickey Mouse has 3 ears, 3 hydrogens, that's your hydronium and cation. And this is the hydroxide. So hydroxide is OH minus anion. So a base you throw it in water forms hydroxide. A Bronsted-Lowry acid is a proton donor, a base is a proton acceptor. This is what we'll mostly talk about in this chapter, what an acid and base is. The best definition is a Lewis acid and Lewis base. Lewis acid is electron acceptor, base is electron donor. How does this work? Well, how do you rip off of a hydrogen from water? Well, if you have the bonding orbital and the antibonding orbital, if you add electron density to the antibonding orbital, that is, the acid will be the electron acceptor, and then the base is electron donor. The base will add electron density. So what I said before holds true. Acid tends to donate positive. Oh, and bases will donate negative charge. Acids donate positive charge by accepting electrons. And biological surfaces are negatively charged, so if you add a base to a biological surface, it tends to expand it, adds electron density to it, expands it. So here is an equation here, ammonia plus water. So ammonia is the base, it means it's a proton acceptor. Water is the acid, it means the proton donor. So that means, so if my smartphone is a proton, this is the acid, it is giving the proton to the base, so the acid is the proton donor, the base is the proton acceptor. And in this case, ammonia accepts a proton from NH3 to NH4 plus, and water loses a proton from H2O to OH minus. So, and in this direction, ammonia is a base. In the other direction, so NH4 going to NH3, it is losing a proton. Ammonium, NH4 plus, that is known as a conjugate acid. And hydroxide is a proton acceptor to form H2O. It's a conjugate base. So you have a conjugate acid, conjugate base. And you can also see water, though. Water, HCl plus H2O makes Cl minus and H3O plus. So water can be both an acid and a base. Water is known as amphoteric. Amphoteric means acid and a base. So what else is amphoteric? Amino acids are amphoteric. So water is not the only thing that's amphoteric, but it's not typical. So identify the acid base and the conjugate acid conjugate base. So we have HSO4, so sulfuric acid plus water forms HSO4 minus. So H2SO4 is losing a hydrogen, that makes it the acid, and the water goes from H2 to H3, it's the base. And in the other direction, so HSO4 goes to H2SO4, that's the conjugate base. H3O loses a proton to H2O, that's the conjugate acid. Same thing, so HCO3 minus plus H2O. So in this case, HCO3 minus is going from H1 to H2. It is the base, it is the proton acceptor, and water is going from H2 to OH. It's losing a hydrogen, it's the acid. And then the other direction, that means that the carbonic acid, H2CO3, is the conjugate acid, and then the hydroxide is a conjugate base. I wrote those in red and blue because of litmus. Okay, let's see if you follow. H2CO3 plus H2O makes H3O plus HCO3 minus. What's the conjugate base? Base is the proton acceptor. It's also only going to be on the right side. The species that is accepting the hydrogen is the bicarbonate there. So HC, hydrogen carbonate, bicarbonate, is accepting the hydrogen. It's the conjugate base. Okay, so weak acids and strong acids. Weak acids are, if you remember in 161, if you had me, we were talking about weak electrolytes and strong electrolytes. Weak acids are weak electrolytes. Strong acids are strong electrolytes. And it's pretty easy to remember them. You just have to memorize the strong acids. Hydrochloric, hydrobromic, hydroiodic, not hydrofluoric, and nitric, perchloric, and sulfuric, but the first hydrogen for sulfuric. These are your strong acids. The rest are weak acids. So if it's not on this list, it's a weak acid. It's real easy to remember that. I typically don't tell you to memorize something. And the way that weak acids work, it's an equilibrium. So we learned about equilibrium last chapter. We're going to deal with equilibrium quite a bit from here on out. So we have a weak acid plus water makes H3O plus and the anion. And the Ka is that. I find it easier just to, and water is a liquid, we don't conclude the solvent in the equilibrium expression. It's easier just to think in HA ionizing and the bottom one here. So I tend to use the bottom one as the equilibrium, just because it's easier that way. And like I said, memorize these strong acids. The one thing with sulfuric, it's a diproduct, 2 protons. It's the first one is the only one that's strong. The second one is a weak acid, so keep that in mind. And some weak acids, hydrofluoric is a weak acid. The reason why it's a weak acid is because it tends to form a dimer. So 2 things, hydrofluoric acid will attach to itself to another hydrofluoric acid, and the attraction there is partially it's because of that, which makes it a weak acid in water. It's still some nasty stuff, so don't get it on you. It'll dissolve your bones. And here's some other weak acids, but we'll talk more about those later. Water will also auto-ionize, so water plus water makes H3O plus OH minus, or H2O breaks apart in H plus and OH minus. The Kw, so the dissociation constant for water, this is the hydronium or hydrogen ion times hydroxide ion, and this equals 10 to the minus 14. K, this is the equilibrium constant for that at 25 degrees Celsius. And you've probably heard of something called the pH. pH is the minus log of the hydronium or hydrogen ion concentration. Maybe you've heard of the POH, it's the same thing, but hydroxide. And the pH plus a POH equals 14. So when you see terms as P something, the sig figs are after the decimal point. So a pH of 12.1 has 1 sig fig. It doesn't have 3, it has 1. It's right after the decimal point. So, and the way pH works is, generally speaking, that 7 is neutral, below 7 is acidic, above 7 is basic or alkaline. So, and pH and hydrogen ion are related by hydrogen ion is 10 to the minus pH, or pH is minus log of the hydrogen ion concentration. So here are some common things about pH. You can see that most food is acidic. So true thing, most food is acidic. Blood is slightly alkaline, not very much. Egg whites are slightly alkaline. There's some milk of magnesia, that's alkaline. But although you can eat milk of magnesia, that's the active ingredients in Rolaids. It's magnesium hydroxide. But generally speaking, most of the things that we eat are acidic. And lime juice is especially acidic. So gastric juice, the pH of your stomach changes. So it's been a while since I've eaten. I'm looking at my clock. It's about 3:40 p.m. I haven't eaten in a couple hours. The pH of my stomach is not 3. It's going to be about 5. My stomach is at rest. After I eat something, the food will stimulate it. It'll get a pH may drop to 1. So it'll drop down. The food stimulates the acid production there. So that's partially true about the human stomach. But let's look at the pH scale. So I mentioned before, pH and pOH are related by the fact that this is just pH. Well, they both equal 14. pH plus pOH is 14. And you can see here that pH of 0 means that 10 to the minus 0, it's 1 molar. You can have a negative pH. It just means that the hydrogen ion concentration is at 10 molar. So, and you can have a pH of 15 as well. It just means that the hydroxide ion concentration is 10 molar. So solution goes from pH 6 to pH 3. How much does the concentration change? So pH is a logarithmic scale. 3 units, it's 10 to the third. It's actually 1,000. So keep that in mind with pH change. It is actually a factor of 1,000. Calculate the pH of each solution at 25 degrees Celsius. Say if it's acidic or basic. A is straightforward. It's just minus log of 1.8 times 10 to the minus 4. And let me just throw that. Oop. I just dropped my iPad there. Let me look at that. So minus log of 1.8e minus 4. And this is, how many sig figs we have? 2. The pH is 3.74, and this is an acid. So B, there is 2 ways to solve B. So the first way is to calculate out the hydrogen ion concentration. So the hydrogen ion concentration times the hydroxide ion concentration is 10 to the minus 14, which means then that the hydrogen ion concentration is equal to 10 to the minus 14 over the hydroxide ion concentration. And so 10 to the minus 14 over 1.3 times 10 to the minus 2. This is 7.7 times 10 to the minus 13 minus log of 7.7 times 10 to the minus 13. So minus log, second answer. And this is 12.11. And that is basic, or alkaline. The second way to do this is to take the pOH. So minus log of 1.3 times 10 to the minus 2 is equal to the pOH minus log, I put natural log, 1.3 times 10 to the minus 2. This is 1.88. So 1886, and then 14 minus pOH equals pH equals 14 minus 1.886. And we get 12.11. So there you have it. There's two ways to do it. You get the same answer. I prefer doing the POH way. You can do the equilibrium way if you want. It's whichever way you prefer. So how do we get hydrogen ion concentration from pH? It's just the inverse of it. So it's just 10 to the minus pH, 10 to the minus 4.8. And we can put that in our calculator, 10 to the minus 4.8. And this is, how many sig figs? 3. 1.58 times 10 to the minus 5 molar. So easy to go back and forth between pH and POH. And I mentioned pH and POH, they sum them together, they equal 14. And when you see a P of something, it just means you take the minus log. So later on we'll talk about KAs. The pKa is 10 to the minus is minus log of the Ka, and you can get the inverse, the Ka from the pKa, 10 to the minus pKa. So that'll come in later. So if you recall, in the previous chapter we talked a bit about equilibrium. So we are going to go through and use equilibrium to solve some problems. So what is the hydrogen ion concentration of a 0.1 molar hydrogen cyanide solution? The Ka of hydrogen cyanide is 4.9 times 10 to the minus 10. So we do this as an equilibrium, 0.100. We shift right, minus x plus x plus x. Equilibrium 0.1 minus x, x. So the Ka is going to be H plus Cn minus all over HCN. And 4.9 times 10 to the minus 10 is equal to x squared over 0.1 minus x. Okay, so, and in doing so, you can look at this. Remember, we can discount this x, so that really small Ka, this is equivalent to x squared over 0.1, more or less. So that means we have 4.9 times 10 to the minus 11 equals x squared. You can take the square root of both sides, and this is kind of 49 times 10 to the minus 12, so this is going to be 7 times 10 to the minus 6 is equal to x equals the hydrogen ion concentration as well. So you can check your calculator if you want for that one. I think it's, because square root of 49 is 7, so, or 7.0 because 2 sig figs. So, but you can use your calculator if you want to verify that. So recap for this one, how do we solve some of these problems looking for various, so pH or hydrogen ion concentration? It's equilibrium. You've learned the skills in equilibrium, so just like the previous semesters, everything you learn you can't forget. So we're going to use the equilibrium expression for quite a bit. And so the same thing, initial change equilibrium. You're going to be using ice charts in this chapter and the next. So anyways, you put in the initial conditions, you have the extent of reaction. We're going to shift right. Extent of reaction, plug in the equilibrium values, write your equilibrium constant, put in the values, solve for your unknown. In this case, we get 7 times 10 to the minus 6 for x. So let's see if you can solve this one out. What is the pH of 0.2 molar nitrous acid? There is a Ka there. So why don't you try and do this while I pause it. Okay, hopefully you've worked on this and tried to solve it out. And what you start off is by writing this equilibrium expression, HNO2 equilibrium H plus NO2 minus. This is considered chemistry common sense. You should be able to take any acid and write out its equilibrium that way. Now you can write your ice chart and start with the initial conditions, shift right, and then write the Ka value, plug in the numbers, solve for x. You get x equals 0.0095 if you discount the x there, and then the pH ends up being 2.018. And that is the end of this one. Come and join me for the next section.